Welcome to the third lecture in cryptography on information theoretic security and the one-time pad. So as promised, we are now going to discuss the implications of perfect secrecy in the one-time pad. If we have that the encryption of M under K is equal to C, that implies by definition that K XOR M equals C, but that also simply says that K has to be equal to M XOR C. And if I XOR both sides by M, then I get that K must be equal to M XOR C, right? This here. And basically what this says is for the OTP that the number of keys in K such that the encryption, if we encrypt a certain message using a key K equals C, that simply is 1. And this holds, of course, for all messages and ciphertexts. So then that implies that the OTP has perfect secrecy. So while this is simple to prove, this provides a very powerful statement that for the OTP, there is no CT-only attack. Unlike other ciphers, the Vigenère cipher or substitution cipher or the rotor machines, all those could be broken by a CT-only attack. So we just had proved that for the one-time pad, that's simply impossible. Given the CT, you simply learn nothing about the PT. The secret key K is too long. If you had a way of communicating the secret key over to the other side, you might as well just use that exact same method to also communicate the message to the other side. So despite having perfect secrecy, that doesn't mean the OTP is a secure cipher to use. And that's an important point. So the bad news is this. So the bad news. So theorem. Perfect secrecy implies that the size of the length of the key space must be greater than or equal to that of the message space. So in fact, another cipher has perfect secrecy, then the number of keys in a cipher must be at least the number of messages the cipher can handle. So perfect secrecy implies that the key length is at least as long as the length of the message. So in particular, what this means, perfect secrecy, that if we have a perfect secrecy, then necessarily the number of keys or the length of the keys must be greater than or equal to the length of the message. So since the OTP satisfies this with equality, the OTP is actually an optimal cipher that has perfect secrecy. But in reality, the OTP is hard to implement and use in practice because of the length of the keys. And so this notion of perfect secrecy says that it doesn't tell us practical ciphers are going to be secure. So in the next lecture, we're going to be replacing the idea of random keys with pseudo-random keys in order to make the OTP practical.